Success is a slow process and quitting does not speed it up. Hi everyone, in this video we'll go through few additional problems from exercise 1.1, problem numbers 7 to 11. You can refer relations and functions playlist for videos specific to this chapter or class 12 mathematics playlist which has all the videos specific to mathematics. Let's take this example. Show that the relation S in the set A of all the books in a library of a college given by the relation is X and Y should have same number of pages, and this should be an equivalence relation, right? What is the condition for equivalence? It should be reflexive, it should be symmetric, and it should be transitive, right? Everything should be true, reflexive, symmetric, and transitive. Only then we can say that the relation is equivalence. Now, what is a set? Set is all books in the library. All the books in the library. This is the set, right? Now, what is the relation here? Same number of pages. The book should have same number of pages. Now, let's say the library has maths, English, physics, chemistry, bio, so on, right? Now, I could have ordered pages as maths and English. Maths and English, probably let's assume that maths and English have same number of pages. Then probably physics and chemistry has same number of pages, right? Just for example. Now we'll check if it is reflexive, right? For reflexive, you should have A comma A belonging to R. The first book, so A is book here in this case, right? A is a book, right? Both are books here and both should have same number of pages. Now if I take, say, 2 maths books could be there, right? I could have multiple maths books. There could be 2 maths books, right? So obviously the pages are going to be same for both the maths books, right? So if I take maths comma maths, both are going to have same number of pages, obviously, right? Same book, just another copy, right? So it's going to be reflexive. So you can say it is reflexive because A and A has same number of pages, right? If I take these 2 books named A and A, both will have same number of pages. Obviously, if I take this as one copy and another copy, both will have same number of pages. Therefore, it is reflexive. Now we'll check if it is symmetric. What is the condition for symmetric? A comma B belongs to R implies that B comma A should belong to R. Now, very simple. Let's take 2 books, maths and say physics, right? We assume that maths and physics have same number of pages. If maths and physics have same number of pages, can I say, I'll just reverse this. Physics and maths. I'm just reversing B comma A. Can I say physics and maths also have same number of pages? Obviously, right? Right? Therefore, it is symmetric. So we'll have to tell it is symmetric because if A and B have same number of pages, then B and A will also have same number of pages. So we can write as R is symmetric because if A and B have same number of pages, it implies that B and A will also have same number of pages. Therefore, it is symmetric. Now we'll check if it is transitive. What is the condition for transitive? A comma B belongs to R. B comma C belongs to R. This should imply that A comma C belongs to R. Now, we'll take the same example. Maths and physics. If maths and physics have same number of pages and B is physics, we'll take say chemistry. If physics and chemistry have same number of pages, can we say maths and chemistry have same number of pages, right? Now, instead of A, we have taken maths. Instead of B, we have taken physics. B is for physics. And instead of C, we have taken chemistry. Now, if maths and physics have same number of pages, and physics and chemistry have same number of pages, can we say maths and chemistry have same number of pages? What is A here? A is maths. What is C here? Chemistry. So can we say maths and chemistry have same number of pages? Yes, right? Therefore it's transitive. So we should write it as R is transitive as if A and B have same number of pages and B and C have same number of pages, then A and C will also have same number of pages, right? A and C, right? That's why it's transitive. Now, since R is reflexive, symmetric and transitive, it is an equivalence relation. Now let's go to the next problem. Show that the relation R in set A comprises of 1, 2, 3, 4, 5 elements given by the relation A minus B is even. Mod of A minus B is even, right? What does mod mean? Mod means even if you put a negative number inside mod, it's going to become positive, right? Basically, the negative number is ignored when you put a modulus symbol. Now, so we'll have to define a relation where A minus B is even and it's an equivalence relation, right? Now, what is the relation here? It is A comma B where A minus B mod is even, right? So we'll take the set A is equal to 1, 2, 3, 4, 5. Now, any element we take in this set, when you subtract them, the number should be even, right? So, example, so relation could be, if I take 1 comma, I can take 1 comma 3 because 1 minus 3, mod of 1 minus 3 is 2, which is even. 1 minus 3 is 2 and it is even. 1 minus 3 is minus 2, but since it's modulus, I ignore minus, right? Then I can also take 3 comma 1, right? Reverse also I can take. 3 minus 1 is 2. Then I can take 2 comma 4, 4 comma 2, 3 comma 5, 5 comma 3. I can also take same numbers, 1 comma 1, because 1 minus 1 is 0 and 0 is even. 2 comma 2, 3 comma 3, 4 comma 4 and 5 comma 5. We could have some more combinations, right? Now, if you subtract any of these numbers, you're going to get an even number, right? So now we'll have to check if it's reflexive, symmetric and transitive. Let's check reflexive. For reflexive, you should have 1 comma 1, 2 comma 2. You should have same elements, right? Now A minus B should be even. Now B also should be same element, right? For reflexive, it should be A minus A. I'm replacing B with A. So A minus A is 0, right? A modulus of 0 is 0 itself. And 0 is even number. So therefore it is reflexive. Therefore it's reflexive. So you should write R is reflexive as modulus of A minus A is equal to 0, which is nothing but is an even number, right? That's all. Now we'll check if it is symmetric. What is the combination? A comma B belongs to R, then B comma A should belong to R. Now what is the relation here? Mod of A minus B. If mod of A minus B belongs to R, can I say mod of B minus A also belongs to R? Basically, it should be an even number. In this case, it should be even number. So, if A minus B is even, then I can reverse it and say B minus A also is even, right? It is even only. Only thing, you could have a minus sign, but because there is modulus sign, that minus gets ignored. So you say R is symmetric because A minus B, modulus of A minus B is even, and also modulus of B minus A is even, therefore R is symmetric. Now we'll take transitive case. In transitive combination, modulus of A minus B is even and modulus of B minus C is even, then modulus of A minus C should be even, right? Now this is the condition, AB, BC, AC combination. Now if I say that modulus of A minus B is even and modulus of B minus C is even, then modulus of A minus C is also even. Now we'll take an example. Say let's take A as 3, B as 5 and C as 1, right? We'll just take randomly some numbers which is there in this set, right? it should belong to this set. So if I take the number, modulus of a minus b is 3 minus 5. What does it give? Minus 2. Modulus of minus 2 is 2 itself. So this is even. Another example is b minus c, right? Another combination is b minus c. So 5 minus 1. What is 5 minus 1? 4. So it is even. Then I'll take AC combination. What is AC combination? 3 minus, this is AC combination, 3 minus 1. What is 3 minus 1? 2, which is even, right? So we have checked that it is transitive. So we can write R is transitive because modulus of A minus B is even and modulus of B minus C is even, implies that modulus of A minus C is also even, right? Since R is reflexive, R is symmetric and R is transitive, we can call it as equivalence relation. Now what is the second part of the problem? Show that all the elements of 1, 3, 5 are related to each other. We'll have to show that all the elements in this set 1, 3, 5 are related to each other. The relation is given here. Relation is modulus of A minus B. We'll have to take this relation, modulus of A minus B. I have set 1, 3, 5. And the relation is modulus of A minus B should be even. Now, you can take any combination. Say 1 minus 3. Modulus of 1 minus 3 is even. Then you take modulus of 1 minus 5. 1 minus 5 is 4, which is even. Then you take modulus 3 minus 5 is minus 2. Modulus of minus 2 is 2, which is even, right? So any combination you take, it's even. So also you can take same numbers. 1 minus 1 is 0, which is even. 3 minus 3 is 0, which is even. So any combination you take within this set, right, it is even, right? Therefore you can say for all elements A, B that belong into set, A minus B also belongs to set. You can call this set as anything, right? Let's call it as set A. Right, we can call it as A. So belongs to A. And modulus of A minus B is even. You can write this. So all the elements are related to within set A because modulus of A minus B belongs to A and A minus B is even. Now same way we can prove that 2, 4 also relate to each other, right? So 2, 4 means modulus of 2 minus 4. There are only two numbers. Modulus of 2 minus 4, modulus of 2 minus 2, modulus of 4 minus 2 and modulus of 4 minus 4. These are the combination that can happen with this two elements. If you see, all the elements would give you even number itself. 2 minus 4 is minus 2. Modulus of minus 2 is plus 2. Right? All of this is going to give you even number. Right? Therefore, you can say all the elements of this set are related to each other by this particular relation, right? You can say all the elements of this particular set 2, 4 is related to each other by this particular relation, that is by modulus of A minus B. Then next part is no element of 1, 3, 5 is related to any element of 2, 4. Now any element of 1, 3, 5 is not related to any element of 2, 4. Why? Now two sets are there. You have two sets. Let's call them as set A as 1, 3, 5 and set B as 2, 4. Now we'll have to prove that they are not related. They are not related. Now if I take one element of this and one element of this, say I take 1 and 2, right? What is the relation? A minus B, modulus of A minus B. If I do 1 minus 2, I'll get minus 1. Modulus of minus 1 is 1. It is odd number. It is not even, right? Therefore, the relation is not satisfied. Therefore, there is no relationship between 1 and 2. They are not related because modulus of those two numbers does not give an even number. Therefore, they are not related. You can take any example. You can take even 3 and 2. You take 3, 2 or 3, 4. It will give you odd number. Or take 5, 2. What is 5 minus 2? You will get 3. If you take 5 minus 4, you will get 1. So every time you subtract any number from this set and any number from this set, you are going to get odd number. Right? Therefore, elements in set A Therefore, set A and set B are not related as modulus of A minus B is not even. Set A and set B are not related as modulus of A minus B is not even. That's all. Now let's go to the next example. Show that each of the relation on set A, x belongs to z. Z means it's an integer, right? That is, you will not have fractions. It will only be numbers, complete numbers, like 1, 2, 3, 4. You will not have fractions. Now x belongs to integers, and that x is nothing but between 0 and 12, right? It's between 0 and 12. It's given by relation. Modulus of A minus B is a multiple of 4. This is one case. And second question is A is equal to B, right? Let's take the first case one. First one. So A is equal to, we can simply write this set, right? It will be 0 and between 0 and 12. So it will be 1, 2, 3 till 12, right? These are the integers. You can also have 0 here because it can be equal to, 0 can be equal to x. So you can have numbers including 0 because it is equal to here, right? And 12 also. So 0, 1, 2, 3 till 12. Now this is a set. Now what is relation? It should be modulus of A minus B should be a multiple of 4. What are the multiples of 4? It should be 0, 4, 8, basically 4 tables. 0, 4, 8, 12, 16 and so on. These are multiples of 4. Now for reflexive, I have to prove that it's an equivalence relation, right? For reflexive, it should be A minus A. Both A and B should have the same elements. A minus A is 0. 0 is a multiple of 4. 0 is a multiple of 4. Therefore, it's reflexive. So you can say R is reflexive because modulus of A minus A is 0 and 0 is a multiple of 4. That's all. Now, similarly, symmetric, right? For symmetric, it should be if A minus B is multiple of 4, then B minus A should also be multiple of 4, right? Now, obviously, right? So, the numbers are reversed. So, when you subtract, you will get the same number because there is modulus here. So, if I say 4 minus, say, if I take 4 minus 0, I will get 4, which is a multiple of 4. Then if I take 0 minus 4 is modulus of minus 4. Modulus of minus 4 is plus 4. So, both the answers are same, even though you reverse the numbers, right? Therefore, you can say relation is symmetric because modulus of A minus B is multiple of 4 implies that modulus of B minus A is multiple of 4. That's all. You have to put this. It is symmetric. Relation is symmetric because A minus B is multiple of 4. This implies that B minus A is multiple of 4. Now we look at transitive. For transitive, modulus of A minus B should be multiple of 4, and if modulus of B minus C is multiple of 4, this implies that A minus C is also multiple of 4. Now take an example, right? If I take A as 0, B as 4 and C as 8. Now if I take modulus of A minus B, I'll get 0 minus 4, which is modulus of minus 4, which is 4. Now I'll take B minus C case, that is 4 minus 8, which is minus 4, which is 4. Now I'll take A minus C case, which is A is 0 minus C is 8, which is minus 8 and 8. Now if you notice, all these three are multiples of 4, right? So it's always true. Whenever you see that A minus B and B minus C are multiples of some number, A minus C also will be multiple of that same number, right? It's always true. So therefore it is transitive. So you can write R is transitive as modulus of A minus B is multiple of 4 and modulus of B minus C is multiple of 4 implies that modulus of A minus C is also multiple of 4. Now since the relation is reflexive, symmetric and transitive. We call this relation as equivalence relation. Now we'll go to the second case. A is equal to B. Relation is A is equal to B. Now for reflexive, what is it? It should be A comma A should belong to R. In place of B, I have put A itself. So can I say A is equal to A? Right? A is equal to A, correct? So since A is equal to A, we can say it is reflexive. That's all. It is reflexive as A is equal to A, and this belongs to R. And this is for every element A belonging to set A. We have been given set A. Now we'll see symmetric. For symmetric, A comma B belongs to R implies that B comma A belongs to R. This is simple, right? A is equal to B implies that B is equal to A. Straightforward. So we can say R is symmetric because A is equal to B implies that B is equal to A. Now we'll see transitive. Transitive is A comma B combination, B comma C combination, and A comma C combination. So here in first combination, relation is A is equal to B. Second combination, B is equal to C. Third combination, A is equal to C. Now, if A is equal to B and B is equal to C, obviously A is equal to C because all are equal here. This means that all are equal. A is equal to B is equal to C. All three are equal. Therefore, it's transitive. So I can say it is transitive because A is equal to B and B is equal to C implies that A is equal to C. The relation is reflexive, symmetric, and transitive. This is also an equivalence relation. Now, the second part of the question is find the set of all the elements related to 1 in each case. In both of these cases, you have to find elements related to 1. For the first case, we'll have to find the related elements which are related to 1. Right? Now, what is the relation for the first case? A minus B should be a multiple of 4. Right? This is the relation. So now, when you say the element should be related to 1, means one of the elements, right? You have A comma B, right? One of the elements should be 1, right? That's when you say that these two elements are related, right? That's when you say that these two elements are related. Now, the relationship is given here. It should be a multiple of 4, right? So, for it to be a multiple of 4, when you subtract A and B, you should get multiples of 4. So, it can be 0, 4, 8, 12 and so on. Now, what should be the numbers, right? The set is having numbers from 0, 1 to 12. Now, what can be those numbers, right? Which can give a multiple of 4 and one of the elements is 1. So, it can be 5, 1. It can be 9, 1. It can be 1, 1, right? 3 combinations are there. 1, 1 is 0, 9, 1 is 8, which is a multiple of 4, and 5, 1 is, when you subtract, you will get 4, which is again a multiple of 4. You cannot take a number greater than 12 because a set does not have number greater than 12, right? So, therefore, set of related elements. So, you have to write set of related elements are 5, 9, and 1. These are the set of elements which are related to 1. So, 5, 9, 1 are the elements which are related to 1. Now, let's look at second case, right? Second relation. Here the relation is A is equal to B and you should find the set of elements related to 1. So, one of the elements should be 1, right? What is the other element? Here A is equal to B. A is equal to B means the other element is also 1, right? Other element is also 1. That's when you say A is equal to B. So, 1, 1. So, what is the set? Set is 1 only because only 1 is related to 1 here. Only 1 is related to 1 here. That satisfies this relation A is equal to B. So, this is the answer. So, let's look at this problem. Give an example of a relation which is symmetric but neither reflexive nor transitive. So, we need to find an example where it should be symmetric but not reflexive and not transitive. So, we know what is the condition for symmetric. So reverse combination should be there. If you have 1 comma 2, you should have 2 comma 1. So simply put a set, call it as R, and take the set as set A. Let set A be 1, 2, 3, and let the relation be 1 comma 2 and 2 comma 1. Now this is symmetric because the reverse combination is there, right? 1 comma 2 and 2 comma 1, reverse combination is there. That's why it is symmetric. Now it should not be reflexive and it should not be transitive. So it is not reflexive because for every element of this set, we have 1, 2, 3. We should have 1 comma 1, 2 comma 2 and 3 comma 3. None of these are there, right? Therefore, it's not reflexive. Transitive. It is not transitive because if 1 comma 2 and 2 comma 1 is there, then you should have first and fourth element. That is 1 comma 1, right? You should have 1 comma 1. So 1 comma 1 is not there. So we are telling R is not transitive as 1 comma 2 belongs to R, 2 comma 1 also belongs to R, but it does not imply that 1 comma 1 belongs to R, right? 1 comma 1, this element and this element does not belong to R. Hence it's not transitive. You can write it as does not imply, or you can say but 1 comma 1 does not belong to R, right? You can say it like this also. You can say it does not imply that 1 comma 1 belongs to R, or you can say but 1 comma 1 does not belong to R. The next one, we will have to give a relation which is transitive but not reflexive and not symmetric. Now, first one, it should not be symmetric means the reverse combination should not be there. So you have 1 comma 2 but you will not have 2 comma 1. You have 1 comma 3 but 3 comma 1 is not there. So the reverse combination is not there. So we'll say R is not symmetric as 1 comma 2 belongs to R but 2 comma 1 does not belong to R, right? So you take the same example, same set, right, and just modify the example. The same example that we took here, just modify it, right, so that you don't have reverse combination. So now we prove that it is not symmetric. We'll also have to say that it is not reflexive. For reflexive, you should have repeated elements in the ordered pair like 1 comma 1, 2 comma 2, 3 comma 3. None of these are there. So therefore it is not reflexive. R is not reflexive as 1 comma 1 does not belong to R, 2 comma 2 does not belong to R, and 3 comma 3 does not belong to R. Now it should be transitive. It is transitive. So if you take 1 comma 2 and 2 comma 3, that means the first and fourth element should be there. First and fourth element should be there. That is 1 comma 3. So 1 comma 3 is there. So therefore you say it is transitive. Now here we have to give an example of a relation which is reflexive, which is symmetric but not transitive. It should be reflexive means there should be repeated combinations. So we have taken this set, right? We have taken set of elements which has 1, 2 and 3. So for reflexive, you should have 1 comma 1, 2 comma 2, 3 comma 3. So this will indicate that the relation is reflexive. So we'll say R is reflexive as 1 comma 1, 2 comma 2, 3 comma 3 belongs to R. That is, for every element A belonging to A comma A belongs to R. Now we'll see if this particular example is symmetric, right? If you have to prove that it is symmetric, you will have to take the reverse combination. If you have taken 1 comma 2, you should have 2 comma 1. If you have taken 2 comma 3, you should have 3 comma 2. So it is symmetric, right? You should have all the reverse combinations. 1 comma 2 has 2 comma 1, 2 comma 3 has 3 comma 2, but this should not be transitive, right? Which means if I take 1 comma 2 and 2 comma 3, here the second elements are same, right? Second elements are same. So for transitive, you should have first and fourth element, right? So 1 comma 3 is not there, right? Therefore R is not transitive. So we should say R is not transitive as 1, 2 belongs to R, 2, 3 belongs to R, does not imply that 1 comma 3 belongs to R. Now let's look at the next one. Here we have to give an example of a relation where relation is reflexive and transitive, but not symmetric. The relation should be reflexive. So straightforward. If it has to be reflexive, we have taken the same set A is equal to 1, 2, 3. So for it to be reflexive, you should have ordered pairs with same elements like 1, 1, 2, 2, 3, 3. Right? So this satisfies the reflexive condition. So R is reflexive as, so for every element that belongs to A should belong to R, which is 1, 1, 2, 2, 3, 3 belongs to R. Therefore, this is reflexive. Now, we'll have to ensure that this particular example is transitive also. Now, and for reflexive, it's easy, right? So, same element should be there. For transitive, you'll have to pick two ordered pairs in such a way that we get the third ordered pair. Now, if you look at, we'll have to take ordered pairs where second element is same, right? Second element should be same. Now, if I take 1, 2 and 2, 2, right? I can take 1, 2 and 2, 2. So here, if you notice, second element is same. So that's how we have to choose the ordered pairs. So what will be the third pair for this? Third pair will be first and fourth elements, which is 1, 2. So here transitive is satisfied. This case, transitive is satisfied. Now you'll have to look for all the possible ordered pairs here, and everything should be transitive. Now again, we'll see if there are any common elements. So if you here between 1 and 3 and 3 and 3, between 1 and 3 and 3 and 3 also, second element is common, right? Now, so what will be the third ordered pair? It will be 1, 3. So here, this one. So this condition is also satisfied. This ordered pair also is transitive. Then we'll have to look for all such combinations. So now with 1 also you can see, right? With 1 also there is a common element with 1. So with 1 you have 1, 1 and 1, 2. 1, 1 and 1, 2. So the second element is same. So what will be the ordered pair? Third ordered pair, first and fourth element. So it's 1, 2. So this condition, this one, this is also satisfied. Now there is another combination with 1, 1 and 1, 3. With 1, 1 and 1, 3. Right? With 1, 1 and 1, 3, you have the second element as 1, which is same. So the fourth ordered pair should be 1, 3. 1, 3. 1, 3 is here. So like this you have 4 combinations here. You will have to look for every combination and you will have to check for transitive. So all the 4 combinations are satisfying here. You have to check for all ordered pairs and then see if it is transitive or not. So now in this example you got 4 cases. So it's better to take where you have lesser combinations. So maybe what we should do is we should remove 1, 3. Right? 1, 3 is not required here. Without that also you can prove that it is reflexive and transitive. Now for example, let me take this relation, right? In this case you will see lesser number of combinations. So here this 1, 3, these 2 combinations will get eliminated, right? Because we have removed 1, 3, these 2 combinations will get eliminated. You'll only get 2 cases, which is easier. So with this set also we can prove that it is reflexive and transitive. Let's check if it is not symmetric. Obviously it will not be symmetric because you don't have the reverse combination. What is the reverse combination? 1, 2, 2, 1. 2, 1 is not there. So we'll say R is not symmetric as 1, 2 belongs to R does not imply that 2, 1 belongs to R, right? You can write it like this or say 1, 2 belongs to R but 2, 1 does not belong to R, right? You can see it like this or you can say it in this particular method. Does not imply, right? 1, 2 belongs to R does not imply that 2, 1 belongs to R. Now let's take this fifth one. You'll have to take an example which says that it is symmetric and transitive but not reflexive. Symmetric, straightforward, right? Take the reverse combination. So 1, 2, 2, 1. So this will satisfy symmetric. And transitive, you should have 3 ordered pairs if you have to prove it's transitive, right? Minimum 3 ordered pairs should be there. Minimum 3 ordered pairs for you to prove that it is transitive. Here you look at the common elements. You have 2 and 2 common. So you have to take first and fourth. You have to take first and fourth as the ordered as the third ordered pair. So it should be 1 comma 1. 1 comma 1 is there. Therefore, this relation is transitive. Do you see any other ordered pair which has common element? The second element and the first element should be common like this, 2 and 2. This is the only combination where 2 is common. Therefore, this is transitive. So you say R is transitive as 1 comma 2 belongs to R and 2 comma 1 also belongs to R, implies that 1 comma 1 belongs to R. Now it should not be reflexive. Reflexive simple condition is you should not have the repeated elements, right? So you have 1 comma 1 here, but you don't have 2 comma 2 and 3 comma 3. So R is not reflexive because for every element belonging to set A comma A does not belong to R. That is 2 comma 2, 3 comma 3 does not belong to R. Therefore, R is not reflexive. Now let's look at this particular problem. Show that the relation R in the set A of points in a plane. So there is a set which has all the points, right? I can say set A which has all points, right? It has all points, say P, Q, R, S and so on. And the relation set is given as PQ, where distance of the point P from the origin is same as the distance of point Q from the origin. That means now say this is origin, right? This is origin. You have 2 points in the plane somewhere, P and Q. Now the distance between this and distance, so if I call this as origin, the distance from O to P and O to Q is same, right? That is OP is equal to OQ, right? OP is equal to OQ. Now, so how will I write the relation here? I will write it as P and Q, where P and Q are equidistant from where? From origin, right? From origin. So this is the relation. You have to prove that this relation is an equivalence relation. So basically here the relation will have multiple pairs. Since the points in the plane are infinite, relation also will have infinite pairs, right? So you could have, say for example, you could have R and S, P and S, right? You could have R, you could have S which is equidistant, right? That is all these distance from the origin is the same, right? And there could be certain points which are far away also in the plane, right? You could have so many points, but these points are not having the same distance as O and P, right? So now all these points are there in the set A, but the relation set, in the relation set you will only have those points which are of the same distance from origin, same distance. So those points are there. So there could be multiple other points, A, B, C, D, E, F, infinite number of points in the plane. Now we'll have to prove that it is equivalence. To prove its equivalence, what you have to say? Equivalence means it should be reflexive, symmetric and transitive. For it to be equivalence relation, it should be reflexive, symmetric and transitive. Now let's first check reflexive. For reflexive, A comma A should belong to R for every point that belongs to A, right? We call this set as A, right? For every point in set A comma A should belong to R. So now in this example, they've given that P and Q are having the same distance from the origin. So you have 2 points P and Q. So as per reflexive, both the points should be same. So P and P, right? Now this P and P, the distance of this point and this point from origin should be same, right? Now the point is the same, right? If I have the point here and if I have origin here, the distance is going to remain the same anytime, right? The distance is not going to change. It's not going to change. The distance is going to be fixed between this point and this point, right? Therefore, I can say it's reflexive, right? So distance from O to P is going to be same. Therefore, I can say it's reflexive, right? So this is reflexive. R is reflexive as P comma P belongs to R, or as P is having same distance from O. From O to P, you write it like this, right? This indicates that it's distance. Distance OP should be equal to OP. Distance from the origin for this point is OP. Distance from the origin from this point is also OP. Both of these are equal, right? Therefore, you say it's reflexive. So R is reflexive because P is having same distance from O, which is nothing but OP is equal to OP, right? Now we'll take symmetric case. For symmetric, it is straightforward, right? If X and Y belong to R, it should imply that Y and X should also belong to R. The reverse combination. So now I have P and Q, which are equidistant, right? P and Q are equidistant from O, right? I will call the distance from P to O as OP and from Q to O as OQ. Let this be the distance. OP is equal to OQ. Now, so if OP is equal to OQ, OQ is also equal to OP, right? What is the relation between Q and P? Relation between Q and P is equidistant. This is the relation, right? It is equidistant from origin. Now, so if OP is equal to OQ, obviously OQ is equal to OP. Does it matter if I exchange these points, whether I put Q here, P here, or P here and Q here? Does the distance vary? No, right? OP is equal to OQ implies that OQ is equal to OP, right? So we say R is symmetric as OP is equal to OQ implies that OQ is equal to OP. Now we look at transitive case. For transitive case, if XY belongs to R and YZ belongs to R, then first and fourth element, that is XZ, should belong to R. Now, for this particular example, what we should do, we'll say distance OP. Let's take another point, say R. So we already have 2 points, P and Q. Both of these are equidistant from origin, right? That is, you have this origin, you have P here, you have Q here. The distance is same, right? Now let's take another point, say R. If I say that OP, distance between OP and OQ, it's already told in the question. OP and OQ is same. And if I say that distance between OQ and OR is also same. OQ and OR. OQ is equal to OR, right? Then can I say that OP is equal to OR, right? This is the first element. This is the fourth element. So basically, if I take this as P, this is PQ combination. This is QR combination. Then I should have PR. I should have PR, right? What is P here? OP. And what is R? What is the distance between O to R? OR. So if OP is equal to OQ, if OP is equal to OQ and OQ is equal to OR, can I say OP is equal to OR? I can, right? Because this indicates that OP is equal to OQ is equal to OR. All are equidistant. If this and this is equal and this is equal, that means all three are equal, right? So I can say, to satisfy transitive, I should say OP is equal to OR. OP is equal to OR. R is transitive as, you can say in two ways, PQ belongs to R and QR belongs to R implies that PR belongs to R, or I can write it as R is transitive as OP is equal to OQ, OQ is equal to OR implies that OP is equal to OR. Now, the relation is transitive, relation is symmetric, relation is reflexive. Now, since relation is reflexive, transitive and symmetric, so we can say it is an equivalence relation. Now, let's look at the second part of the question, which says that show that the set of all points related to a point P which is not equal to origin, right? Origin is 0, 0. Other than the origin, all the points related to point P indicates that circle is passing through point P with origin as center. Now, if you have points, say, P, Q, R, S. P, Q, R, S, which are equidistant from origin, right? The distance is same, right? If you have set of points which are equidistant, it simply indicates that is circle, right? Only circle is one such geometric figure where all the points on the circle are equidistant from the center or from the origin. So we can say, since all the points have the same distance as OP, let's call the distance between OP as D. So if you have set of points where the distance from those points to origin is D, then we can say that the circle passes through point P with center as origin. With this, we've come to the end of this particular topic. We will solve some more problems in the next video. If you like this video, do press a like and share it. Thank you.